Now let us understand the factors on which the electrolytic conductance depends. The first factor is the nature of the electrolyte. See, the electrolyte or the salt which we are taking must be a strong electrolyte. It should dissociate completely, so that whatever the moles of the electrolyte has been taken, it is going to give the corresponding number of ions out of it. So it must dissociate completely, or in the other words, we can say that it must have a least solute-solute interaction. So the ions are able to behave individually, and they can migrate to their respective electrodes independently and without the effect of the other ion which is there in the solution or in the electrolyte. So the electrolyte must be strong. This is what is the meaning of the first factor is. The second factor is the size of the ions produced and their solvation. The next most important is that the size, what type of the size the electrolyte is giving. The ion size again is very important. See, the ions basically are like very similar to the ants which are carrying their load and they are moving towards their target. In a very similar way, the ions carries their charges and they move towards their respective electrode. Now, if the ion is very bulky, fine, it can carry more amount of the charge, but since it is bulky, the speed with which it is moving will be far less. Then it will be of not much of importance. Similarly, when suppose the ion is of very small size, of course, fine, its speed will be very large, very high, but the amount of the charge carried by it will be not very large. The fraction of charge carried will be very small. And that is why we have to correlate between the two, and that is why the size should not be very large and should not be very small. And what we find is that is why we have a term specifically which is not there in the syllabus, which is called transport number, which takes care of both of these factors. So size, though is important, should be not very bulky, it should be moderately or smaller, as small as possible, so that the speed is very high. And the other important thing is that it should not get solvated to a very great extent, because then once it gets solvated to very great extent, what happens is the size again becomes very large. We can take the example of this one to best describe is that we know that the smallest alkali in the +1 oxidation state is your lithium ion, and the largest is your cesium ion. But the moment we compare their size in the aqueous medium, what we find is that the largest alkali in the +1 oxidation state in the water or in the aqueous medium is your lithium, because it gets maximum solvated. So it becomes so much bulky, whereas the smallest is cesium. And since cesium and rubidium therefore are rare earth metals, the only next element which is possible, which is having a small size in the aqueous medium and is able to conduct very large amount of the charge, is the potassium ion. That is why in the salt bridges we use as potassium ions. So this factor deals with this. Next is the nature of the solvent and its viscosity. The solvent should also not interact with the solute other than the ion dipole interaction, so that it gets what it is solvating it. And the most important, the solvent-solvent interaction should not be very strong. If it is very strong, the viscosity of the solvent will be very high. And once the viscosity is high, the ions will face a lot of resistance towards when they are moving towards their respective electrodes. So higher is the viscosity of the solvent, higher will be the resistance faced by the ions. So the solvent, the nature of the solvent should be like this. It should have a least viscosity. Then concentration. We believe that more the ions we will take, more will be the conduction. It's not like this. Remember, electrolytic conductance is inversely proportional to concentration, because smaller are the ions, more will be the interionic space between them, and more freely they will be able to move towards the respective ions. And that is why what we find is that the electrolytic conductance is inversely proportional to concentration. Of course, this is actually will be taken separately in more detail later on. Then temperature, yes, as the temperature is increased, the kinetic energy of the ions gets increased, so they move towards their respective electrodes with a much faster and a much higher speed. So what we find is with the increase in the temperature, electrolytic conductance increases, so it's directly proportional. So all these are the factors which affects it, and we try to include all these factors into the formulas or the terms which are actually typically used for this purpose. So now after understanding the factors, let us start use the terminologies which are used in this, and the first term used in this is called conductance.